Hello and welcome back. So in this chapter, chapter number one, we'll talk about what exactly we need to discuss as well as the project assigned to this chapter. But before I do that, I would like to just very briefly go over our Canvas site. Now, in your particular case, the Canvas site might look slightly different because every semester we modify a little bit here and there. But on the left-hand side, you might have different kind of tabs. In my case, you might see a home tab. From there, you can look into announcements, course syllabus, and modules. So the module is the one which is very important one because that's where you can see the course information. And this is where our textbook is available. The textbook is available for free. You can download, you can read online. If you would like to download, the PDF file is available simply by clicking on it. You should be able to access the book. And we'll go over the book just in a bit. And additional information you can find, sorry, the textbook is right there. This is the course syllabus. The textbooks, you can simply click on this PDF and you can download the textbook right there. And then you can find my contact information, and then you can find that based on what kind of course I'm teaching, either 5 weeks, 8 weeks, 12 weeks, or 16 weeks, because we offer different modalities and different kind of weekly basis in each semester. So it is divided into modules. So you can see the modules are right there. And you can find the resources. So under the resources, you might find PDF, for example, for that particular week. If there's some software is needed, any video lectures are available for that week, and what are the assignments we. So I'm going to go to module 2 just to show you. In module 2, you can see chapter 1 PowerPoint is available. You can see the video lectures are available. In your case, it might be just one video lecture. If there are any demo files, I'll be uploading the demo file and the project associated for that particular week and for that chapter. You can see the project number 1 is, now this is from the fall semester. You can see the due date. If you're taking a winter class, the due date will be different, of course, and spring it will be different. So you just need to look into the due date for that particular week under that module. So this is how everything is organized. So now I'm going to share my PowerPoint with you, and you can see the PowerPoint. Let me just double check. Um, I believe you can see the PowerPoint, but I'm going to double check again just to share again, just to make sure. All right, so now the PowerPoint is visible to you. And you can find that all the PowerPoints are already available on our Canvas site. You can review them at any time. So I'm going to go over this chapter. At the end of the chapter, I'll be sharing with you a project, what project, how to complete that project, and what software to use. Although in different times, we recommend different types of software. So when it comes to the software, I'll discuss that one with you as well. So during the PowerPoint, I will not be going over every single detail because that is something you need to read the chapter number 1. And the chapter number 1, I'm going to drag the book here. And let me just double check so you can see the book. So here's the book. And if you go to chapter 1, so this is where the chapter 1 is. And you can see this is the page number 2. And if you zoom in, you can find additional details. So I will be skipping some of these details. For example, here on page number 2, it says brief history of overview and history of the computers, some of the devices at different dates. It is your responsibility to read the details here. So, for example, Charles Babbage in the early 1800s, who he was and what kind of device he invented and what is the impact on that one. Then gradually it moves on to, on page number 3, some of the devices built by IBM and so on and so forth. So that's just wanted to highlight that not every detail will be shared. So I'm just double checking that you have access to my PowerPoint. So not every detail will be shared per se, but when you read the chapter, all that information will be available to you. All right. So in the in the second, in the objectives area, different types of computers and some of the information you might find pretty straightforward and easy to understand because we have been using hardware and some software. And probably after maybe 15 minutes or so, that's where we pick up the information about languages and software. That should be the focus of this class as well. Discover what a compiler is, and that's the word we use very frequently. That's the program which basically converts a high-level language such as C++ into machine language. Then we'll write our first program together, and we'll move forward from there. So without software, so this is our first slide, intro slide, and the computer is basically useless. Software basically are instructions telling the computer what to do. So in fact, when you have a set device or set machine in your access, for example, a vacuum cleaner or a microwave oven, you have some limited options on those machines or devices. But what if you have the flexibility that you can give instructions and the machine can behave accordingly? So that's what the software is. Software is basically telling the computer what to do. Without the software, computer is just like has no real purpose. So software is developed by using something called programming languages, and there are hundreds of programming languages. I have taught more than a dozen programming languages. In fact, in a typical semester, I teach Python, C++, Java, and in the past, I have taught Visual Basic, C Sharp, many other programming languages. Some of them you're familiar, some of them you're not familiar. In our particular class, we'll be using C++ as our programming language. That is our main focus. And C++ is a general purpose programming language, can be used for solving various kind of problems, all sorts of problems. In fact, many of the newer programming languages are developed by C++. Many of the operating systems are developed by C++. So C++ is comes from the family of languages. Originally, there was a language in 1971 called C language, and C++ was kind of emerged in the industry around early 80s, around 83, 84. And then from there, many other languages were influenced by C++, such as Java and C Sharp. So these languages, if you learn one of these languages, you can learn, it's very easy to transition to another language. From C++ to Java or from C++ to C Sharp, it's a very kind of similar kind of programming syntax. Of course, there are variations. The libraries are different. Some of the functionalities are different, but transition is pretty simple from one language to another language. This is the page I was showing you earlier in the textbook. So this is the early calculation devices. These devices were used for various purposes. So if I make a transition to the book again, right there, and you'll find the first computer-like machine was Mark 1. This is page 3. But if you go earlier, right there, I just want to show you the abacus is a system built sliding beads in a rack for addition and subtraction. In 1642, this French philosopher and mathematician Pascal invented the calculating device called Pascaline. So those are the details you need to go through. In 17th century, this inventor invented a device to do simple add, subtract, and multiply and divide. In 1819, Joseph Jacquard, a French weaver, discovered that weaving instructions for his looms could be stored on card with holes punched in them. So these were all different iterations in the history of inventing different types of kind of calculating devices. So when you read about it, it gives you maybe a one or two lines of understanding that how these individuals were kind of instrumental developing the modern computers, what we use these days. The modern computers were invented in 20th century, about I would say 100 years ago or so. But even the Babbage calculating machine or analytical machine was pretty significant, and you should read maybe a half a paragraph or so about that one as well. Right? So let's move to the next screen, and that's where These are the devices in early 20th century, Mark I, ENIAC, and UNIVAC. They look like the computers we can recognize, but these were very large machines. They use vacuum tubes, and they actually were housed in gymnasium-like rooms. Very significant amount of energy was used, and many dozens, if not hundreds, of people actually uh, operated on these machines. These machines were slow, and many of the storage mediums were punch card, which were mentioned in on that page I was reading. The punch cards allowed us to store about maybe 100 characters per card. So they had the punch card. I actually used to have punch card, and I used to demonstrate in my classes as well, and they had 80 columns, and each column slightly more than 80 columns, but each card could store about 80 characters, which is a very small amount of information. But this is how we were making transitions from the early system to the newer system. And in the 1960s or so, the transistors were invented. The transistors were kind of in the pipeline, but the transistors became widespread in 1960s. And if you watch the older movies from 60s, you will see that people are holding their boom boxes on their shoulders. And in 1970s, that headphones were became with the Walkmans and those kind of things, and those were because of the transistors. What the transistors did, they made much larger vacuum tubes much smaller. They condensed the technology into much smaller scale, and suddenly in 1970s, now we have digital watches and other devices. And gradually, with the collection of hundreds, if not thousands, of transistors, we came up with microprocessors. And this is where we have a lot of these transistors. Transistors is basically how to control the flow of the electrons or the electricity. And now we were able to invent the microprocessors. And now today's microprocessors, they have billions and billions of transistors in one device, which is pretty significant. So microprocessors gave us the ability to create much faster, modern computers. Initially, we had mainframe and mini-frame computers. Then we had mid-sized computers. We used to call them servers. And then in 1970s, late 70s and early 80s, companies like Apple and Microsoft and other companies, IBM, they started introducing microcomputers. Microcomputers are basically personal computers. We call them PCs these days. And then gradually, the rest was the history because at that time, those visionaries, they had this vision that in the future, people will be using personal computers. And those are the personal computers we have these days. So in the next few slides, I'm going to skip some parts. I'm going to discuss some other parts. They're pretty simple and straightforward. So basically, it shows what are some of the basic elements of the computer system. The hardware are basically something you can touch, such as a keyboard, a monitor, a device itself. All these are different types of hardwares. Inside the computer, there is something called CPU, which is central processing unit, which is the brain of the computer. And the brain of the computer is connected to the main memory called random access memory, RAM. And then we have also something called secondary storage. Secondary storage is your hard drive, maybe these days we call them thumb drives, or we also do some kind of cloud storage. Those are different types of secondary storage. Secondary storage, just for your understanding, is permanent storage, like it's non-volatile, versus main memory, which is volatile. It needs source of energy all the time, so it is kind of temporary memory. That's another name you're going to see in chapter number 1. It is temporary memory because as soon as there's no source of energy or electricity, all the information is wiped out. Then we have input-output devices. Next slide or so, we'll talk briefly about it. I'm going to skip those slides because they're very simple and straightforward. Your keyboard is an input device, your monitor is an output device, and your printer is an output device, and so on and so forth. Our main focus in this class is the software. Software is basically the program, or we call them code, or call them instructions. That's where the main focus is. And in this class, we'll learn how to develop our own software. All right, so again, a little bit more about CPU, central processing unit, which is the brain of the computer, and main memory is the RAM. and some of the other things I have already mentioned. So this is your central processing unit, brain of the computer, most expensive piece of hardware in your computer. So if your computer is worth maybe $500, your CPU probably will be worth $200 to $250. So it's a very small chip, but that's where all the processing takes place and all the delegation, all the responsibility and management of the software happens in the CPU. CPU also has something if you divide the CPU into other components, you will find control unit, something called ALU, arithmetic logic unit. Arithmetic logic unit or ALU, it allows you to do the logical decision making, rational decision making, computation, and those kind of things. And it's an important component within the CPU. So, like I stated, there's a control unit, there's an ALU, arithmetic logic unit, and these days we also have something called cache memory, L1 cache, L2 cache. Those are built into CPU. Just want to highlight, just so you understand that memory is not part of the CPU. Memory is an outside entity which resides outside of the CPU. So, but CPU is constantly works with the memory. In this picture, you can see this purple area. That's where the CPU is, and the memory is outside. So there's constant communication takes place between CPU and the main memory. Other name for the main memory is RAM, random access memory. And you can see these are the input devices connected. That's how you can communicate, and then you can produce the results with the help of the output devices. Notice that the secondary storage, which is typically a hard drive or SSD or a thumb drive or cloud storage, that is also an outside entity. All right, so random access memory directly connected to the CPU. All programs must be loaded into main memory before they can be executed. This includes your videos, browsers, video games, any other app, any other website that must be uploaded in the RAM or main memory. All data must be brought into main memory before it can be manipulated. Here, manipulation doesn't mean some kind of bad term. It means just the processing needs to take place, and that's what the manipulation here is. When the computer is turned off, everything in the main memory is lost because it's volatile. It needs a source of energy all the time. Unlike the secondary storage is permanent. Whenever you store something there, it is even if there's no source of energy, you can always access it, such as something you carry on your thumb drive or on your hard drive. So main memory is an ordered sequence of memory cells. Each cell has a unique location. So later on in our class, I'll demonstrate how you can actually see the memory addresses. And memory addresses are typically shown in hexadecimal format. And we'll learn in chapter 2, probably briefly in this chapter, or maybe in chapter 2. Typically, the humans, when we do interaction, we use a decimal number system. The computer itself or any digital device, they basically use the binary number system. Binary number system has base of 2, 0, and 1. Decimal number system base of 10, 0 through 9. Then we also have something called octal number system base of 8, 0 through 7. And hexadecimal has a base of 16, 0 through 9, then A, B, C, D, E, and F. I'll show you how the memory can be seen with the address. Each cell has an address assigned to it. In C++, you can actually directly see the memory addresses as well. So each cell can contain either a programming instruction or data. Let me spend maybe half a minute or so just to explain it to you. A lot of people confuse data with an instruction. Data is not an instruction. Data is a raw fact and figure a number such as 25. 25 is piece of data. Instructions is what to do with the data. Instruction is basically a program, a code. So basically instruction given by us or given by AI these days, and it grabs the data and does something with the data. For example, if I take all the ages of a college students and say, with the other instruction, take all of them and give me the average age. So the data is all the ages of all these thousands and tens of thousands of students, and then grabbing them, adding them together, dividing them, and calculating the average, that is the instruction. So instruction is basically calculating the average. The data is all different ages. And I might end up with, let's say, 24.5. That will be the output in that particular case. So secondary storage, it is permanent. It is called non-volatiles, and some of the things you probably recognize, hard drive, you probably recognize flash drives or thumb drives. You probably don't use floppy diskettes. I did use them. I used zip disks. I used CD-ROMs for storage. I used tapes for storage. In fact, the first ever program I stored when I was a kid, I used to store in a regular cassette, in a tape. And even before that, we used to store on punch cards. These days, most of your storage is probably in the cloud, somewhere on Google Cloud or some other cloud, and that's how you're storing the data. Now, input devices, I don't need to spend too much time, such as keyboard, such as your mice, your secondary storage. I wouldn't say this is an input device. This is like a stretch to it, but I'll just I will disagree with an author, but it's there. Monitor and printer, these are your output devices. Okay, so this is where our class begins. This is where our main focus would be, and we'll be spending a significant amount of time understanding the software. Software are basically instructions. They tell the computer what to do. So according to this slide here, the programs that do specific tasks, perform specific things based on those instructions. Now, there are two major types of software. One is called system software, and other one is called the application software. The system software are the operating systems. We will not be writing system software in our class. In fact, we are familiar, such as Windows operating system or iOS or Android, or these are the operating systems. Some of you probably have used Linux or Unix or some of the other operating systems. There are very few operating systems out there. There are other operating system software as well, such as device drivers, utility programs, and even some authors, they put programming languages as system software as well. System software are very complex, very difficult to create. They should work with so many different devices and different kind of environments, and they are not easy to manage. They are very complex. Of course, you can write smaller system software, such as a utility program to do something on your particular machine. You can write those, and those are not very hard to write. But we are talking about the larger operating systems, OSs. Those are very complex, and very few exist in the world. And they monitor overall activity and management of your entire device. So they do the device, memory management. They do control the input and output activities, all the storage management, among thousands of other activities. So these are very complex. Our focus will be on application software. Application software, there are in millions, if not hundreds of millions out there. In fact, we will be writing application software in our class, several of them. And some of the examples you recognize, such as games and spreadsheets and browsers, and all these are application software. Your PDF documents, your Word documents, and all these are different types of application software. Now, there are different types of signals. We humans, when we talk, we use analog signal. Our sound is not very digitized the way we talk. It goes up and down, and it is like a continuous wave. On the other hand, the digital signals are exact and discrete, zeros and ones. Zero means there's no source or there's no electricity or current, and one means there's some energy or some current. So that's what the digital signal is. Digital signals are very discrete and exactly the same. So our machine language is a language of a computer, and it uses only the digital signal, only the binary code. Computers do not understand English language or Spanish or Chinese or none of these languages. Computers only understand if the energy is there or electricity is there or electricity is not there. That's all. But if we can understand zeros and ones, and initially machine language or machine code was written in that format, but it was very tedious, very difficult to manage. Then gradually we learn maybe we can create some instructions, and those instructions can be converted into ones and zeros. That's where the programming languages were initially introduced. And we're going to go through the hierarchy of these programming languages just in a bit. So your binary digit is digit 0 is off, and 1 it means on. So whenever you see 0 as a binary digit, it means the off. And whenever you see 1, it means on. And your machine code or binary code is basically sequence of ones and zeros, or zeros and ones. All right. So your byte can store one character at a time. And byte is a collection of 8 bits. 8 bits are make one byte. So byte can store one character. Now, when you say one character, it means such as uppercase A, that's a character. So this one character, A, for example, uppercase A can be stored in one byte. And byte is a collection of 8 bits, 8 bits. Okay, and these bits can be turned on and off. And when you turn on certain bits, we can we have created this a fictitious chart. We call it ASCII chart, which is going to come up just in a bit. And we have assigned specific values for each one of these characters. Whatever characters you see on your keyboard, we have assigned values. For example, uppercase A, we have assigned a value of 65. And 65 is a little bit more meaningful for a computer because in the previous screen we saw the computers only understand zeros and ones, as you can see, 0 and 1. So maybe 65 can be converted into ones and zeros. And that's where the bits can be turned on and off. And so we'll come back to that one just in a bit. So if you have collection of 1024 bytes, that is called 1 kilobyte. It's not exactly 1000, it's slightly more than 1000, 1024. And then I mentioned that one ASCII chart. ASCII chart, let me open up an ASCII chart and show it to you what the ASCII chart looks like. If you simply type ASCII and go to images and pick up one of these, let me open this one up. This is an ASCII chart, and I'm not too sure you can see it, so I'm going to exit and share separately just to be on the safe side. So this is an ASCII chart. So this ASCII chart basically allows me to see uppercase A is right there, a value of 65, as I indicated earlier. Notice that the lowercase a has a value of 97 in decimal. The middle, the yellow column is the hexadecimal. We'll talk about that one later, but as you can see, uppercase A has a value of 65. And that can be converted into ones and zeros in a byte. All right, let's go back here. Let me go back to my slide. All right. So now you can see that that's what the ASCII chart looks like. And the people who created this ASCII chart, they gave the fictitious values. Like I stated, all the characters on your, or all the buttons on your keyboard, they have an ASCII value. For example, 0 is 48, spacebar is 32. And each one of these other punctuations, they have ASCII value assigned to them as well. ASCII stands for American Standard Code for Information Interchange. There's another one, IBM uses ABSTIC. It's going to come up just in a bit. But there's another one, which is the newest one called Unicode. Unicode is going to become the international standard because Unicode has an ability to store more characters. In case of ASCII, the maximum code we can represent in 1 byte are 256. Because if you have 8 bits, 2 to the power 8, the maximum possibility is 256. But what if I want to represent other languages? And other languages, they have different characters which are not readable in English language. So then Unicode uses 2 bytes. By using 2 bytes, we have an ability to store many, many more characters. We'll see that in just in a bit. All right, so this chart here shows a byte has 8 bits. A kilobyte has 1024. Mega, M for million. Giga is 1 billion. T for tera, T for trillion. So 1 trillion bytes. And just to let you know that these days when you go and buy a computer, your hard drive typically, or your SSD, is 1 trillion or 2 trillion or 2 terabyte or 3 terabyte or higher. When I was using computers, the storage at that time was in kilobytes. And when I finished my college and I bought a $3,000 computer, it had only 2 gigabyte hard drive. But these days we are in 1,000 times have more storage as far as hard drives are concerned. We also have petabyte. By the way, the difference between each one of these units, between zetta, exa, peta, is 1,000. So if you have 1,000 terabyte, it makes 1 petabyte, and so on and so forth. So the difference is 1,000. And AppStick, as I mentioned earlier, is used by IBM. It also uses 1 byte to store the characters. The Unicode I had mentioned earlier can uses 2 bytes. 2 bytes mean 2 to the power 16, 65,536 characters. So this one actually will become an international standard because it has an ability to store more and more characters. If you are interested, I can show you what the Unicode uh, charts look like. So if you simply Google Unicode, and let me see if I can find the charts, they always change the place. Um, Let me see if I can find it. Okay, code charts. So you can see all these languages are already represented in Unicode. So all the languages, and I can read 4 or 5 languages. I can tell you if you just pick any random language, and you can see the values and the characters in that particular language. For example, this particular character has a hexadecimal value of this 08A2, which is basically Gene. Gene is like J in English language. So this letter is can be represented in Unicode in this format. So other characters of other languages can also be represented in Unicode. So Unicode is much better than any other ASCII or AppStick. Okay, just for your knowledge, and again, when you read the book, it will make a little bit more sense for you. Okay. Did I miss anything? Okay. Yeah, that's good. So initially, like I stated earlier, we were using machine language. Machine language was very cumbersome to write all ones and zeros. Then gradually we developed something called assembly language. And this is what the early machine code looked like. So if you want to calculate wages equals to rate times hours, so everything must be the instruction and the code and the data must be in that kind of format. So that is very hard to understand. Imagine if you just want to change one value or you want to change the rate or hours, it would have been very cumbersome. Then gradually we developed a low-level language called assembly language. Now, assembly language instructions they had some keywords. So instead of ones and zeros, they came up with some keywords such as load, such as multiply, such as store. So now you can declare something called variable. Variable is some kind of value for that particular piece of data. And then you can assign that variable, you can load it, you can multiply the rate with hours, and you can store in wages. So assembler is the program which translates assembly code into machine code. So and some of you will learn assembly when you take CS51, either at Long Beach or another college or maybe a university. So you might take it with us, or you might take it in a university, but you will learn about a little bit about assembly language. Assembly language is low-level language. It is the fastest and most efficient one because it is very close to the machine language, but still we use assembly language. It has limited keywords, but it has some benefits as well. We are not going to learn assembly in our class. We are going to learn only C++, but just to let you know that assembly language is still in function. Then gradually around 1950s, the first ever programming language was invented or introduced and called Fortran, Formula Translator, and then that gave birth to many other programming languages. Normally, I show a chart. In fact, it is available on our Canvas site. You can see the programming language chart. And if you're interested, how each one of these languages, when they were introduced and the influence on other languages. And my our focus here is C++. By the way, I know all of them. I have programmed in all of these languages, and I have taught all of them as well. But we will be learning in our class C++. C++ is one of the most powerful languages. And in fact, anytime you simply Google the top 5 programming languages in the world at any time, any year, you'll find C++ is one of them. And C++ will allow you to understand how the programs work and how you can use C++ to write any kind of code, create a new programming language, or maybe a game, maybe a business application, maybe a website, any kind of program. And C++ program, when it's written in that language, it must be compiled. So there's a program called compiler. The compiler translates the C++ code, which is a high-level language, into machine code. Now, high-level language means that, remember that human languages are very abstract, such as English or Spanish or Chinese. They're very abstract languages. Machine language, on the other hand, on the opposite part of the hierarchy, it is very discrete, 1 and 0 only. And then on top of machine language, you have assembly language. And on top of that assembly language, you can have something called high-level language. We used to have middle-level languages as well, which we don't discuss anymore. But high-level languages are all of the languages you probably have heard: Python and Java and C++, and all those are high-level languages. Above high level languages, you will hear something called visual languages. Above visual languages these days, you might even hear something called AI languages or AI code. So our goal is to understand that compiler is a program which is going to convert my C++ code into machine code. And it does behind the scene. In my demonstration, I'm going to use an online compiler, but you might be able to use Visual Studio or Xcode or any other kind of compiler as well. So in C++, the same instruction we saw earlier can be written like this. So there's a variable called wages, which is equal to rate, this is a multiplication symbol or operator, and multiply with hours. Every C++ line of code ends with semicolon. Just like in English language, you have a period. In C++, it's semicolon. So this basically translates to some kind of processing. You're taking hours and multiplying with rate and storing them in wages. By the way, this same exact code will work in Java as well, C# as well, and C language as well. So you'll find a lot of commonalities between these languages. All right, let's take a look at the first ever program. So here's our first ever program. So in fact, I'm going to demonstrate that one. If I run this code, it's going to show me my first C++ program. And this particular line of code, and I'll explain what each one of these things mean, belong to this function. So main is a function. And also when we use these in any language, in C++ or Java or these languages, we also include some libraries. And by the chapter 3, we'll understand what these libraries are. But the libraries are basically a collection of some of the instructions. So we tell the compiler, when you don't understand certain things, if you want to know what cout means, go to this particular library. And this IOStream means input-output stream. It's a collection of different functions or statements or objects. So it basically tells the compiler can goes to IOStream library and figures that out. Now, namespace STDs, STD stand for standard, also is a collection of different kind of steps. If I don't use namespace std above the main function, then every single time I have to write std colon colon scope resolution operator for each one of these. And that is very cumbersome. To avoid that one, we simply say using namespace std above the main function. All right, I'm going to show you how do I run this code in my environment. So I'm going to go to, let me see if I have, yeah, let me just open up this one here. So I already opened up here. I'm going to come back to that one just in a bit. But if you want to search, you can simply say C++ compiler. Just type C++ compiler, Google that word, and you're going to find a lot of online compilers. I do recommend highly these days to use an online compiler. Although the textbook and my previous lectures might indicate Visual Studio or Xcode or any other piece of software, if you feel comfortable using those software, that's perfectly fine. But these days, things are changing so quickly that if I record a lecture in a specific environment, let's say Windows environment in Visual Studio, which is a product of Microsoft, half of the students will not have access to Windows-based computer. They might have a Chromebook. Then 25% might have some kind of Mac or Apple device. So then it becomes very confusing. And they say, well, I tried to follow your instructions. I don't understand it. So in order to avoid all that confusion, a few years ago, I just started using online compiler. So I recommend you can use an online compiler. You can simply click on this one. It's going to open up something like that. And it runs directly in your browser. Also, and let me open up this clean one. Let me also highlight that a lot of students, they did not know how to install Visual Studio or Xcode or some other software on their personal devices. Believe me or not, many of the students, even online students, did not have personal computers. And you say, well, how that's possible? They did not have personal computers. Well, many of the students, they either borrow from the college or high school, or they just use your phones and they try to run the software on their phone. So that's why explaining them, spending a week or 2 weeks or something, wasting all the time downloading the software, I decided I'm going to make a switch. I'm going to go to the online compiler. So when you're in the online compiler environment, which I just showed you, I just cleaned it up a little bit, and this is what it looks like. So you have something called include IOStream using namespace std int main. Don't worry too much about it. Curly brace open, curly brace close. That's exactly what you see in our program in our slide show as well. So in order to display something, you can simply say hello world. Typically, that's how we say it. Whenever we start a new programming language, that's like a tradition. ENDL. ENDL means basically new line, end line. Cout means display or print. Console out. Console out means whatever I show you in double quotes, just put it on the console. And ENDL, give me a new line after that one. So when you run this code, you will find the results right there. Let's say I want to write another line of code. I can go underneath. I can say, and by the way, notice the semicolon at the end. Semicolon indicates that's where this particular statement or sentence of that language has ended. So here, if you say California and double quotes close, and then I want to do ENDL, and I'll talk more about these in lesson symbol. This is some of these operators, and all these languages, they have certain grammatical rules or syntax rules. So the people who created this language, in order to separate one type of instruction from the other type of instruction, they have these less than symbols, especially for output purposes. When it comes to input, these operators change sides, and we'll talk about that one just a little bit later. So now when I run this code, you'll see two lines of code, two lines of instructions right underneath, or two pieces of outputs are there. So you can see how easy it is to use this compiler. Simply click a run button, and it produces the results over here. You don't have to install anything. You don't have to worry about I have Mac versus Windows or Chromebook, or I don't even have a computer. So none of those excuses will work in our class anymore. And I remember that when we had to install software, the first 2, 3 weeks, some of the students did not even submit work. They said, well, I'm going to pick up the computer from the lab or from the college and so on and so forth. So now we don't have those excuses. In that way, we can do our work more efficiently. And uh, this slide shows to execute a C++ program, use an editor. So in our case, that's where when I was typing out the code, that is called the editor. And that code is called source program. The code I was writing, such as cout, less than, hello world, that is called source program. Source program is something written in high-level language, such as C++. Source program is readable. It's easier for us to learn some basic instructions and write that source code. But those computers do not understand source code. They must be compiled. So the source programs must be compiled and also linked with the instructions. So the preprocessor directives, they typically start with number sign. These are basically the libraries. So we are telling the compiler, if you don't understand something, use the library I'm including, such as IOStream or namespace std. So then the compiler checks the program, obeys the language rules. We call them syntax rules. Then everything goes well. If everything is fine, then it translates into object code. Object code is the machine code. So object code is the machine code. All right, so source code is written in C++. That's what we are going to learn in this class. Once it's compiled, compiler compiles it, it becomes an object code. By the way, this particular code will have the extension of .cpp in our case. And this code, when it's compiled, has an extension of .obj. It is still not fully independently functional, but at least if the compilation happens successfully, it means the program, the compiler did not find any errors in our code. Then it links it. Linker, there's a program called linker. It combines the object code, obj, with other programs provided by the SDK. SDK is basically your package system development kit or software development kit. It basically compiles along with some of the libraries it has. And those libraries contain pre-written code. For example, some functions, some of the statements which we have been provided. Imagine when you buy a phone or a device of any kind, there are a lot of pre-written code already embedded for you. All you have to do is customize according to your own desires. But that's pre-written code. It comes from those libraries. Once it has successfully linked everything, then the program is loaded into the RAM, random access memory. And the loader loads into main memory, which is the random access memory. And then it is executed. If the program is executed successfully, then it has an extension of .exe. Remember, we started with an extension of .cpp. Then after the compilation, it becomes .obj. After linking the library and loading, it becomes .exe. Exe is the file which runs independently. So then in our case, luckily, we didn't have to worry about all those things because this particular online compiler did everything for us behind the scene. It basically converted a source into object code. It basically did the linking. It basically loaded. It did everything for us. So, but if you are in a Visual Studio environment, you probably will see these things separately, and you probably see some of these things separate files as well. Right? So that's just very basic stuff. Now, here, the same instructions we have discussed in last few slides. Editor is the place where you write your C++ code. Then the preprocessor basically tells the compiler what kind of instructions which are being used, so it can refer to those libraries. Compiler, if it finds a syntax error, syntax is a grammar error of that language. Just like your English teacher will say, well, grammatically, this is incorrect. Can you fix it? So you will go back and fix it in the editor. Come back, compile again. If there are still errors, it will send you back. So you will fix all the errors. If the errors have been resolved, then the library will be added, link by the linker, link the library. It will be loaded into RAM and the program will be executed successfully. This can further be into this particular cycle. This is one of my most favorite word in the world, and the word is algorithm. So this is the reason you're taking this class. You're trying to become an individual who can solve a problem. So algorithm is a step-by-step process of solving a problem. If you develop an algorithm, in the world of AI, you'll be very marketable. That's what the companies are going to look for. They're going to look for the problem solvers, the people who are critical thinkers. So algorithm is the key for our class, that you become a problem solver. But in order to solve a problem, you have limited resources. You have limited time, limited number of people, and limited amount of money. You cannot say, okay, I'll solve this problem in 100 years. Not possible. So solution must be achieved with limited resources. So algorithm has two things. You're solving a problem with limited resources. And what exactly the problem is? Well, if you look around you, if you look at on the right-hand side, this chart here, the problem could be your 4-year college degree. Then you put analysis. You say, how do I solve this problem? You can divide it into year by year or semester by semester or week by week or daily basis or hourly basis. You can analyze and then you make a plan for it. So that's where the algorithmic design is going to come. Once you feel this algorithm is going to work to solve that problem in a limited time and resources, then you start coding it. Once the coding actually is done, then you do the pre-processing, you do the compilation, the linker links the libraries, load it into memory, execute it, and the final results. If all the errors have been resolved, you have the final results. All right. So analyze the problem, outline the problem and its requirement. A lot of time is spent on this particular issue because if the problem is not properly analyzed, you will not get the proper solutions as well. So you must have a high level of algorithmic mindset to solve that problem. And most of the people, many of the people lack this in their life. When you lack this particular issue, you're going to waste time and you will not be very successful. So please understand, you're here in my class to develop this algorithm and then implement the algorithm in code, verify the code works, and use and modify the program if necessary, if you want to make any changes and so on and so forth. Thoroughly understand the problem and all the requirements of the program require any interaction from the user. User need to provide you data into what kind of processing you have to do, what are the outputs. If the problem is complex, I like to call it compartmentalization, basically divide into smaller problems. The smaller problems are easier to solve. Analyze algorithm for those smaller problems. Check if the algorithm works, check for the test with the test data, and check if the mathematical analysis are needed or some kind of computation is needed. So once the algorithm is designed and correctness is verified, write the code in that particular language. In our case, it will be C++. The high-level language we are using is C++. And then place the code in the text editor and go through the sequence which I have shown you earlier. Run that code in a compiler. If the compiler generates error, look at the code and remove errors. Run code again through the compiler. If there are no errors, compiler generates the machine code. Then linker links the libraries and it's loaded into memory. And the final step is the execution. And the compiler guarantees that program follows the rules of language, does not guarantee that you'll have the correct results. Because if your algorithm is incorrect, and syntax is correct. Syntax means the grammatical rules have been followed. It's going to give you the results, but the results might not be accurate. So compiler does not guarantee the accuracy of the results. Compiler only guarantees that the rules of the language are followed. I'm going to show you my own example just in a bit. And this is the example shown here. If you like to read in the book, you can read it, but I'm going to show you my own example. And so the last thing before I show you my example, and I'll talk about Project-1, is there are two major methodologies. One is called structured methodology, one is called object-oriented methodology. Most of our class will be spending on structured methodology. In Chapter 10, we'll talk about object-oriented methodology. Most of the modern languages are object-oriented. In structure, dividing a problem into smaller subproblems, implementing the structure design. And the structure design basically is top-down, stepwise refinement. It's a modularization of your program. Basically, divide and conquer. That's the whole idea in that particular case, because if the problem is very complex, you divide it into smaller pieces. On the other hand, the other methodology, which is called OOD, object-oriented, you divide or identify the components called objects, such as you identify customer as an object, you define product as an object, building as an object, and then these determine how these objects can interact with each other, how an employee going to interact with a customer, and specify relevant data and possible operations. So there are two things. Data and operations are built into the objects. So it's a slightly different way of writing the code. And we'll come back to object-oriented in Chapter 10. Then it will make more sense at that time. An object combines data and operations on the data into a single unit. The programming language which implements OOD is called OOP, Object-Oriented Programming Language. C++ can behave both ways. On the other hand, Java is purely OOP. Python is OOP. All the modern languages are object-oriented programming languages, but C++ can behave both ways. Write a program algorithm and implement them in a programming language. Use functions to implement. And again, this might not make too much sense at this level here, but gradually after Chapter 9, all the rest of the chapters are in object-oriented development methodology. And I'll show you how to create a class. From the class, you can instantiate different objects, which will make more sense later on. So this is an older slide, but it basically tells you that who invented around 1983, one of the European, he created this language. Many different C++ compilers are available, and so on and so forth. All right, so I'm going to now show you, before I show you the code, let me jump directly into, and I think you can see we are under Project-1. If you click Project-1, and if you read the instruction in Project-1, it will tell you, get the user input for ID, hours worked, rate per hour. 3 inputs from the user. And I'm going to show you how to take those 3 inputs. Then the results should include display ID, hours worked, rate per hour, and gross pay. So this is our project. And in this project, write a simple program that displays a title, employee salary records, insert comments in program to document the program internally. And I'm also showing you some sample here. This is not exactly what it looks like, but I'm just showing a similar sample. This is the expected output. Expected output should look exactly like this one right there. And I'm showing you a screenshot of the expected output as well. So under Project-1, you'll find all the necessary information. This is what I'm looking for Project-1. And you'll be uploading 2 files for Project-1. One is the output screenshot. You're going to take a screenshot by using a snipping tool or taking a picture with your camera, with your phone, or print screen, whatever method you know how to take a screenshot of your computer. You'll grab a screenshot showing me your results, output results. And the second file you're going to upload is the CPP file. I'll explain both of them here. All right, so we know this is our code, and we know this is what my output is. So on my computer, let's say this is my final output for project 1. I want to grab this output. I have something called snipping tool. I can open up the snipping tool. I'm not sure it's going to show up on your screen or not, but I will click new, and I can actually grab this output here. And this will basically allow me to upload this particular screenshot. Now, my program is of course not complete. What if my program assuming it's complete? If I want to copy this one, Control C, I can copy it, copied my entire code. I can open a Word document or TXT file, Notepad. Uh, Notepad is a simple one, and I think you might be able to see it. Let me see if I can capture it. And let me just double check. So I can dump my code right there. So I copied my code from my online compiler, copied and pasted, assuming this is my complete functional program, meeting all the requirements for project 1, which it does not, but right now let's assume it. Then I can save this file, save as. I can say file, save as. And let's say I want to put it somewhere, and I want to call this file .cpp. So how do I do that? So I'm going to put double quotes, project1 .cpp, double quotes close. What it does by putting the double quotes, it's going to force this file to be saved as CPP file. CPP stands for C++ file. So you're going to upload this file and the screenshot of your results. Okay. I already showed you how to capture screenshots. You can use a camera if you don't have any tool. I use snipping tool on my computer, or you can use a print screen on your keyboard as well. Print screen is typically very close to the backspace button. So that's the file you're going to upload for your code. Without your code, I cannot verify anything. I cannot verify your program. I cannot verify anything. I must have your code in order to give you any credit. Secondly, I must have your output file, the results as well, the screenshot of your results. You do not have to upload a screenshot of your program because I cannot run your program from the screenshot. I must have the screenshot of only the output or the results. But the CPP file will have your code in there. All right, having said that, let me show you how do you declare a variable, which we'll be discussing in chapter 2 later on. But here I'm just going to show you how do you declare a variable. And I will not be explaining everything in detail, but if I want to use a whole number, such as ID is, let's say, assume a whole number in that organization, I can declare a whole number like this, int for integers. Integers are basically whole numbers, and they are available in C# and Java and C and C++, many other languages as well. And let's say I want to call this variable ID. ID is created, which is an integer, which has an ability to take a whole number. Then I also want to create a variable for rate and hours and gross amount. For those in C++, we call something called double. Double is a real value. Real value is something which has decimal places. Potentially, it can have a whole number or a decimal value. Let's call it rate. Rate. Then I'm going to have something called double hours. Then I'm going to have one more, double gross amount. Okay, so I declared altogether 4 variables. One variable is of integer type. 3 of them are of double type. Why? Because the integers are only whole numbers, like 1, 2, 3, 4, 5. Rates could be 25.55. Hours could be 40.36. Gross could be 800.79. So that's why you need to declare them as doubles. Now, already have shown you how do you display something on the screen. The opposite to see out is see in. See in. So see in means I'm going to take the data from the user. Notice that this time the operator are changed. This one is values going out. This one is value is coming in. Now, if I'm taking something from the user, I must store in a variable. In a variable, I have declared successfully variable ID, so I can take something from the user right there. As I can see from the instruction, I need to take an ID from the user. I also need to take something else from the user, something called rate. I also need to take something from the user, something called hours. All right, so I'm taking 3 inputs from the user, 3 inputs. All right, I have declared 4 variables and I'm taking 3 inputs because this gross will be calculated in our code. So right now, I will not be taking this from the user, I'll be calculating it. So if I run my code, it's going to be very confusing because the compiler will be asking for value, but how do I know what exactly is asking? Because the user is not going to see the code. User only sees the blinking cursor, and user doesn't know, are you asking for a first name? Are you asking for age or social security number? What exactly you're asking? So that's not a good idea. So I should go back and right before ID, I should prompt the user. I should say, please enter your employee ID. When I do that, and if I run my code, then it makes sense. Take a look over here. Now it's making sense. It says, please enter your employee ID. I said, oh, yeah, I can do that. My employee ID is, oops, I ran too quickly. Let me run again. My employee ID is, for some reason, it's not letting me type that information. Very strange. Let me try to do it again. Okay, I'm going to use that side pad was just giving me trouble. Let's say my ID is 1, 2, 3, 4, 5. That's my ID. I hit enter, and now it's asking for something. I don't know what it's asking for. So again, the same problem. So I'm going to go back, stop my program, and right before my rate, I will say see out. I'm going to prompt the user, please enter your rate per hour. So it's very clear to the user what exactly I'm asking. And outside of this double quotes, put semicolon, do the same thing. I'm going to copy this one. There's a lot of copying and pasting in programming. Please enter your hours worked. Now we have all 3 prompts and all 3 variables. Now when I run my code, everything will make sense. Here's my ID. Here's my rate, 25.565. And here is my hours worked. I worked 40.5 hours. And here it is. Notice that it did not calculate the gross salary because I did not tell it to calculate the gross salary. I'm going to let you do that. I'm going to let you calculate the gross salary and display all the results. How do I display the results? Exactly like this one. Exactly, your output should look similar to this one. You should be displaying your name. Should displaying the name of your program, the date you have written the program, the name of your college, and all other information. That will be your project number 1. Once your project number 1 is completed, you're going to upload 2 things for me. One is the code I already showed you, but I'm going to show you once again. You copy it, highlight, Control C to copy, or you can right click and hit copy. Go to some kind of software such as Notepad or Word or other kind of software. Paste it there. and I already showed you, but I'm going to show you one more time. You can paste it in that one right there. I just pasted it once it's complete. And then you can simply file, save as I indicated, you can put double quotes, project1.cpp, double quotes close, hit save. It's going to save that particular program as CPP file. And similarly, if you feel that your program is working as expected, you're going to upload the screenshot. And the screenshot, let me come back and talk about the screenshot one more time. The screenshot, you can use a snipping tool or a print screen or your camera. This is a screenshot of your output. Okay. So that will be due in the first week when you read the first chapter and when you can understand the chapter, what the processing needs to happen. So my program is not complete. You still need to calculate. Again, when you read the chapter, it's going to tell you how to calculate. In fact, we saw in slideshow in multiple places, how do you process something, easy stuff. Remember, gross is really easy. Gross equals to. In the slideshow, we saw wages. I'm using a variable called gross. It doesn't really matter. It's just a different name. So then you will multiply rate with hours. Then you start displaying all the outputs. Make sure you also display your name, the name of the program, the date, name of your college on the top. All right. I think that covers everything we needed to cover. And hopefully you'll be able to upload that successfully for first project. And once the first project, let me also show you, I know some of you might say, well, I don't know how to, let me just try. Let me just go as a student view. So there's no issue whatsoever. So I'm going to share my screen one more time. Okay. And I will let me stop sharing for a second. I think I closed the screen. Okay, now screen is open. Let me try one more time. Okay. And let's see. For some reason, okay, I think it's right here. Yeah, let me, yeah, some reason it's not letting me bring that screen, but I think I think you can see it because I have multiple screens and sometimes it confuses me which screen is being recorded at this time. So when you go there, I'm going to go as a student. So when you go as a student, you'll find underneath, when you're ready to upload your project, you will find somewhere. Oh, I'm not. Yeah, it's not letting me show you, but typically submit assignment. There's a button called submit assignment and leave student view. And when you click submit assignment, it's going to open up a place where you can upload your files. If you have any difficulty, I'll work with you separately, but should not be a problem. All right, so we'll end right here and I'll see you in the second chapter. Thank you. Bye-bye.